Hi everyone, I'm Yu-Hsuan Huang. Today I'm going to talk about our work on the compressed oracle technique and post-quantum security of proof of sequential work. This work is also accepted for publication at QCrypt 2021. Let's first give a brief overview on what we are going to talk about today. First, we are talking about the quantum random oracle model. Then, we give a brief summary of our results. As a commonly used technique, we are talking about lazy sampling in both classical and quantum settings. Finally, we will discuss our results in more detail. So the random oracle model is a common way to analyze classical cryptographic scheme that use a hash function. Here, hash functions are idealized into uniformly sampled functions, and everyone has access to. In the quantum random oracle model, everything is pretty much the same, except now we have quantum access. That is to say, the query data points can now be in the superposition. We are also in the context of parallel queries. Parallel queries are in the contrast of sequential queries, in which adversary is only allowed to ask for the output of one data point for each query round. While in the parallel queries, adversaries are allowed to ask for the outputs of multiple data points at a single query round. However, we require that the queried data points to be non-adaptive in a single query round. That is to say, in a single query round, these data points should not depend on their queried outputs. A typical example problem in the QROM model is the so-called zero-preimage problem, which asks to find the input x that is mapped by the hash function to 0. It is well studied and understood in both classical and quantum settings. For example, executing Grover search in parallel is known to be optimal for the parallel queries. Another example problem in the QROM model is the so-called hash chain problem, which asks to find a sequence of data points x0 to xq such that one is mapped to another. We refer to this sequence being a hash Q chain. As we can see, finding a hash Q chain should be easy with Q sequential queries. However, it is expected to be hard if the number of queries is less than Q. Even if we are given parallel access to the random oracle, because now the data points are non-adaptive, so it should also be hard. To show the hardness for hash Q chain problem is easy in the classical setting. However, there hasn't been any quantum proof, at least prior to our work. So what is our work? We give a useful framework for analyzing such problems in the parallel query QROM model. Using our framework, one can prove quantum hardness of these problems using classical reasoning. And this works by recycling probability bounds from the classical proof and lifting them into the quantum proof whenever applicable. For demonstration, we apply our technique into solving various example problems. This includes simplifying existing proof, such as the hardness for zero-preimage, and also obtain new bounds, such as the hardness for collision finding problem and the Q-chain problem. As a main application of our framework, we also give the first post-quantum security proof of the PoSW scheme proposed by Cohen and Piasrat in 2018. So the PoSW scheme, or the proof of sequential work scheme, is a cryptographic primitive that that is important in the context of blockchain. In the PoSW scheme, prover tries to convince the verifier that a certain amount of sequential computation work has been done by the prover. Independent and concurrent to our work, Blocky et al. Also managed to show the post-quantum security for the PoSW scheme as well. Remark that there are several differences. First of all, their proof is rather tailored to the specific PoSW scheme, whereas our proof is more generally applicable to more problems. And second, to understand their proof, a certain amount of quantum information science is required. Where in our work, assuming the framework is correct, verifying our post-quantum security proof for the PoSW scheme is just a matter of purely classical reasoning. Next, let's talk about the lazy sampling technique, a commonly used technique for analyzing the random oracle model. So, we can basically simulate a random oracle using a database instead of sampling the entire function at the beginning. We think of the database as initially empty everywhere, and whenever an entry is being queried, we sampled a fresh randomness for that entry. To put it more formally, the database is modeled as a partial function with augmented value but, meaning the but will mean that the entry is being empty. And of course, after Q queries, the obtained database will contain no more than Q non-empty entries. An important observation for this example problem, the zero-preimage finding problem, is that if there is no zero within the database, dq, where q meaning that the number of queries, then the adversary is unlikely to output one such zero preimage as well. His best guess is to find some input x that is not recorded within the database. However, since x is not recorded in the database, its output will correspond to an unknown fresh randomness to the adversary. Therefore, this will succeed with probability no more than an exponentially small bound. So here we have the formal bound reducing the probability adversary success into probability database having a zero within, with only an exponentially small error term. We can now put this into the quantum setting. It is the way to understand Zendry's compressed oracle technique in the sense that now the database are in the quantum state, and whenever an entry is being freshly sampled, we use Zendry's compressed oracle to sample that entry. Formally, now the state of database is in the superposition of partial functions, of course with less than q non-empty entries after q queries. We also have similar observation here. If after q queries we obtain the database dq by measuring the database state, and there is no zero within the database, then the adversary is unlikely to find a zero preimage neither. Except now the error term is slightly different. Although this simulation is non-obvious, it is a way to understand the compressed oracle technique. Next, let's talk about a classical analysis for the zero preimage problem, and keeping in mind that our goal is to eventually lift them into the quantum settings using our framework. We have already reduced the probability adversary success into the probability database having a zero preimage. But how do we bound this probability? So here we make two observations. First, we observe that if after Q queries the database from but to DQ, now having a 0 within some of its entry, then that 0 must occur during one of the Q sequential queries. So we can now bound the desired probability by sum of the probability database sampled from not having a 0 to having a 0. And we will denote this maximal probability as in this bracket notation, where we code the transition capacity. And second, we observe that whenever a database is transitioned from not having a zero preimage to having a zero preimage after one parallel query, then the 0 must occur within one of the queried entry. So we can therefore use a union bound to bound the transition capacity as follows. Putting things all together, we can now bound the desired probability. For the second observation, we introduce a new terminology here, namely the transition from no zero preimage to having a zero preimage is strongly recognizable by local properties 0. We refer to the database property 0 as being local because it only depends on one entry of the database. Now we can put this proof into a higher level. So the recipe is basically as follows. First, we decompose the desired probability database having a bad event P into sum of transition capacities. And second, we bound the transition capacities with respect to the probability of local properties that recognize the transition. And in our framework, the recipe is pretty much the same, except now we are in the quantum setting, so we have different definition of the transition capacities, and correspondingly the adjusted formulas for bounding these transition capacity and probabilities. So first, similarly, we can also bound the square root probability of database having a bad event by the sum of transition capacities. And second, we can bound the transition capacities by means of recycling the classical bounds from previous classical proof and plugging into our formulas to obtain a quantum bound. We also have different kind of recognizability. For example, in case of a weaker notion of recognizability, we can bound the transition capacity by these formulas. However, the point is, it's just a matter of recycling probability from classical proof and plugging into the formulas to obtain a quantum bound. Now let's see how we use our framework to prove the hardness of zero preimage problem in the quantum setting. So first, recycling from classical analysis, we obtain the local properties and its small probability bound. And second, by plugging in our probability of local properties into the formulas, we can now bound the transition capacities from not having a zero preimage to having a zero preimage. And the transition capacities summing together will bound the desired square root probability. Putting things all together, we can now bound the database having a zero preimage with probability no more than 10q squared k over size of y. So this bound is sharp in the sense that by executing Grover's search in parallel, the success probability for adversary will actually meet our asymptotic bound. The punchline here is we don't need to understand the definition of transition capacities. It's just a matter of lifting classical proof into quantum proof. By using essentially the same recipe, we obtain several additional results, such as the hardness for collision finding problem and the bound for Q-chain problem. It is also worth mentioning that the hardness for collision finding problem, this bound is in fact sharp because there is a collision finding algorithm called the BHT algorithm, and we can parallelize this algorithm so that the success probability finding a collision actually meets our asymptotic upper bound here. As a more complex application or a main application of our framework, we prove the post-quantum security of the non-interactive variant for the PoSW scheme constructed by Cohen and Piotrak in 2018. However, here in the PoSW scheme, the situation is more complicated because now we cannot use the same recipe because the PoSW scheme, even in the classical proof, classical analysis, will need to consider intertwined crude problems such as collision finding problem, Q-chain problem, etc. And therefore, we actually need a tool to decompose these intertwined problems and their corresponding transition capacities. That's why we are giving calculus for the capacity. For example, we are giving basic rules to manipulate the quantum transition capacities, such as first, the transition capacities are symmetric because we can always uncompute the Oracle query. And second, whenever there is union properties within the transition capacities, we have something like quantum union bound for the upper bound and also lower bound for that. Similarly, when encountering intersection property, we can also bound the corresponding transition capacity as well. These rules are relatively intuitive, and we also have more involved but useful rules for transition capacities. For example, when sequentialize a parallel query, a parallel transition capacity into multiple transition capacities, we can add in an conditional property with only several penalty terms. So this allows us to work with the transition capacity on an abstract level without understanding the definition of the transition capacities. And here we can always use classical reasoning, purely classical reasoning. Finally, let's give a recap on our contribution. By means of abstracting away technical aspect of centuries compressed oracle technique, and also proving new technical results for parallel queries, we offer a useful framework that help us prove the query complexity bounds in the parallel query Q-Rong model. And this works by using purely classical reasoning, by recycling probability bounds from classical proof and lift them into the quantum proof whenever applicable. For demonstration, we also apply our framework into solving various example problems, such as we recover known results, such as the hardness for a zero-point problem, but also find new bounds, such as hardness for collision finding problem, for Q-chain problem, and also the post-quantum security of PoSW scheme. That's it for today. Thanks for listening. And by the way, we also encourage the audience to visit and read our paper for more detail.